Bonjour, bonsoir, bon après-midi, wherever you might be. Today it's my great honor and pleasure to welcome my mathematical brother, the co-organizer of the seminar, Frédéric LATRÉMOLIÈRE from Denver. He will tell us everything and more about the Gromov-Hausdorff hypertopology for proper quantum metric spaces. But before I give the floor to him, because let me say that four of us are here in Sydney right now. So we were very moved, very touched by the Bondi Beach massacre, which happened right here only a few days ago on Sunday. Therefore, I request that you join me in a minute of silence in honor of the victims of this absolutely unspeakable massacre. Thank you, Frederick. It's all yours now. Take it away.
Thank you, Piotr. So thank you very much for the invitation and to the other organizers. And it's my pleasure to have the opportunity to present my work on quantum metric geometry. And this is going to concern a very, very fresh preprint that I just put on the archive. So it's, I would say, the unrefined straight out of the research project discussion on specifically the locally compact aspect of non-commutative metric geometry. So let me just take it away for us, hopefully. Up, make sure my little techno gadget works. Okay, there's a bit of a lag. All right, so of course, this audience is well versed in the idea that non-commutative geometry is a general idea founded on the allegory that certain non-commutative algebras, analogs of algebras of functions on a certain type of spaces. That's very generic. And for fun, today I decided to go with a few quotes to, instead of me telling you what I think should happen, let people significantly better than me tell you that. So Paul Dirac, in his book Quantum Mechanics, for instance, said that we shall see later, that's later is in the book, that in spite of this fundamental difference, where we refer to non-commutativity, the dynamical variables of quantum mechanics still have many properties in common with their classical counterpart, and it will be possible to build up a theory of them closely analogous to the classical theory and forming a beautiful generalization of it. I'll let you be the judge of how beautiful today is, but you could see that this is an old concept, if you want. Non-commutativity gained particular interest outside of mathematics because of quantum mechanics, and the idea of trying to generalize classical theory to these algebras of observables is old. Now, my personal interest is in non-commutative metric geometry, which is founded on the same allegory, but the non-Q algebras analogs of algebras of Lipschitz functions of a metric spaces, so a little bit more narrow and well-defined focus. And keep that in my image in mind when we define what a quantum compact metric space or locally compact metric space is, because it will look like an algebra of Lipschitz functions. Now, if I have to try and find the root of this particular subdiscipline, I would quote.
Frédéric, if I
Yeah.
might jump in. That's a very beautiful quote of Dirac. It's good to refer to classics, but something is wrong with the camera. And because in this recording, the only person who is visible is the speaker, it would be
Oh, I
good if
see.
one face
All
would
right.
be visible.
It's very important I'm visible. All right. So Kohn said in a paper in Ergodic Theory and Dynamical System in the 1980s, I believe. In this paper, we shall work at the C-star algebra level, that is dealing with non-commutative analogs of compact spaces, such as the duals of discrete groups. Actually, I will only give you examples with cross product, but whatever. We shall develop for such spaces an analog of a notion of metric on a compact space. Examples include ordinary, not or, sorry for the typo, ordinary compact Riemann manifolds, as well as the duals of discrete groups on which a word length function is specified. So this was when Alain Kohn started to say, well, if you have a spectral triple, whatever that may mean, it contains metric information. A bit later on, Mark Riffel, I will call my advisor by his first name as a reflex, started to take that proposition maybe seriously, that is really focusing on the metric aspect. And started this in a paper in the 1990s where he said that Kohn has shown us that Riemannian metric on non-commutative spaces, namely C-star algebras, can be specified by generalized Dirac operators. That's what now we refer to as spectral triples. Although in this setting, there is no underlying manifold on which one then obtain an ordinary metric, Kohn has shown that one does obtain in a simple way an ordinary metric on the state space of a C-star algebra. So that was, of course, it's referred to as a Kohn metric typically in this context. But this metric, as Mark noted, generalized a Monge-Kantorowicz metric on probability measures. So we went from the idea that spectral triple in some sense defines some sort of metric to the idea that this metric, in fact, is an analog of a well-known object in probability theory with a whole slew of properties that maybe we want to borrow from the classical picture and import to the non-commutative realm. So that's a philosophy that will underlie a lot of the talk today. Now, what do we do with compact chronometric spaces? I mean, it's nice to define the concept, but it's also nice to have something interesting following. And well, sorry, the quote is complete, but it's barely fitting. Actually, that is definitely on Mark. Mark was interested, I believe, from the get-go in devising a topology on the class of chronometric spaces, or some classes, I would say, of chronometric spaces. And so here's the motivation that started the story. When one looks at, again, from Mark in this memoir of the AMS in 01, when one looks at the theoretical physics literature, which deal with string theory and related topics, one finds various statements to the effect that some sequence of operator algebras converge to another operator algebra. Then there is a square bracket, a little ellipsis here. Mark goes on to give various examples in the literature. And so I summarize this by all of this suggests that there are metric considerations involved in their convergence of algebras, and that one is perhaps dealing with some kind of convergence for corresponding quantum metric spaces. Within the mathematical literature, the only widely used notion of convergence of ordinary metric spaces of which I am aware is that given by the Gromov-Hausdorff distance between metric spaces. Okay, so that's the shortest history and contextualization of my talk. Over the years, we went from it would be nice to understand algebra functions, non-coherent algebras as some sort of generalized algebra functions. Alain Kohn specifically told us where we could go, how we could start something like that, if in particular the sort of spaces we look at are metric. Mark Riffel took it to heart to really work on that, and then eventually proposed that this could be useful for things like these, where we can talk about convergence of algebras in a new non-commutative geometric sense.
Very good question, Adam.
Yeah, please. Oh, sorry. Yeah, I will be very bad with this, so please interrupt me at any time. Go ahead.
Yeah, so these examples coming from physics, do you mean these fuzzy spheres? It was the first historical example?
mean, historical example for Mark's distance or for
sequence of operator algebras converging to something.
I don't think it's the only one. I mean, I'm certainly aware of examples involving the quantum tori, for instance. So I would be hard pressed to tell you which one started first. I mean, for instance, if you look at the book of Weil, Andre Weil, you will find in it a chapter on finite quantum mechanics, and it involves fuzzy tori. So it goes back a long time. Yes.
Okay, interesting. Thank you.
Yeah, you're welcome. Yeah, I should say that even though Mark mentioned string theory, this was around the time where Alan Cohn, Douglas, and Schwartz published a paper on compactification in string theory, where actually some of these quantum tori approximated by fuzzy tori showed up. So this was, in the air. But I would say that this is also for finite quantum mechanics. This is interesting, possibly my own theoretical interest, not what I'm going to talk about today or what I have yet to work on, but would be more quantum field theory. I mean, the idea of finite models approaching limits is natural. The idea that Mark wanted to emphasize is that if you're a physicist, there is a natural underlying geometry to your problem that such ideas as I discussed until now might be able to capture better than more ad hoc ways of converging consistent algebras. There are, of course, many different ways and notions to approximate these algebras, from inductive limit type things, AF, AT, etc., to or even MF or whatever, to things like nuclearity and quasi-infinity, to continuous fields. But this is different because this involves additional structure of a geometric nature and generalizes the theory of convergence for geometric spaces used actually quite extensively in actual Riemannian geometry. So from a historical perspective, this quote comes from the paper of Riffel, where he constructed the first analog of the Gromov-Hausdorff distance. But his distance, which was very interesting and actually is topic of my dissertation at the time in 2004, could be zero between quantum compact metric spaces built on top of system algebras, which were not necessarily isomorphic. So this is not a surprise because Mark's construction was not in fact on system algebras, but done on the, I don't know how to say, broader class of operator unit spaces. So the multiplicative structure played no role, only the order. And so immediately that spurred a whole lot of variance as I was a graduate student, such as the distance divided by k immediately using operator system in place of operator space or order unit spaces, Wei Wu using operator spaces instead of operator systems. Those are sort of matricial things. Li and Feng Li, my historically one of my two closest brother from Mark, worked various versions actually, and then Kerr and Li worked together. So there was a whole industry early in the 21st century on how to address this by basically changing a little bit the notion of a quantum compact metric space and adjusting the convergence of Mark to their new settings. Okay, then it becomes a little bit more self-serving. After a few minutes of talking about the giants, we're now talking a bit more about the speaker. So I actually, after my dissertation, did not work in this for a decade at least, but for about a decade. But then I came back to it and just about 12 years ago, introduced yet another variant, but this variant was defined specifically to deal with quantum compact metric spaces built on top of system algebras together with the analog of Lipschitz seminorm that shall be defined later in the talk, having some sort of Leibniz inequality, your familiar product rule. This actually, believe it or not, I'm not going to go over that unless I'm asked, was a source of grave difficulties, by which I mean there's a reason why nobody did it before, and there's a reason why Anfang proposed something close, Anfang Li proposed something close, but still, other than that, there were issues either with the Leibniz property of system algebras where if you were trying to force it too naively, I would say, you lost certain properties of your distance. It wasn't a distance anymore, triangular inequality failed, or wasn't complete, or something failed. So this gave us the first real example of a complete metric up to really the right notion of full quantum isometry. That is really the base since algebras are actually the same. Topologically equivalent to the Gromov-Hausdorff distance. I will define those words. If you don't know them later, don't worry. But for my introduction, I want to give you a context and universe in which all of this takes place. So this propinquity is equivalent topologically to the usual Gromov-Hausdorff distance from usual compact metric spaces. And you can do stuff with it. For instance, there is an analog of Gromov compactness theorem, and there's a whole bunch of examples. I don't think I need to read them all, but it's somewhat related to the question I had a minute ago, and that gives me an aside to say, if you have a question, please ask, because even though I've taught on Zoom way more than I wanted to, I never took the habit of looking at little hands. I prefer that you just interrupt me or the chat, because I tend to look at my slides. Anyhow, the matricial approximation of quantum tori is an example that I just referred to, and the question was about matricial approximation of continuous function on spheres. Second bullet, you have continuity. Really, the third and first point are in the same paper, but quantum toris themselves from a continuous family. You have continuous families of nice AF algebras like F of Shen in their natural parameters, things like non-commutative tori, things like curved quantum tori introduced by Dabrowski and Sitars, etc. I mean, try to give examples here of some people that may be attending, or at least maybe attached to this group. And then it can go further. So this slide,
Sorry, I have a question.
Yes, please go ahead.
Could you give some non-examples, some family which somehow it was believed that it would be continuous, but it turned out to be not?
I don't have one on top of my head. That doesn't mean it's not there. I think the focus has been to actually prove examples. I mean, you see, sorry, my little clicker here. I'm going way out of my thing. Because of the theorem I mentioned here, you really do need the limit is unique. So there's really some rigidity to this thing. So can I think of an example where it fails on top of my head? Not really. Well, yeah, I mean, okay. But it's more related to this slide now that I think about it. But so in the metric sense, so the actual propinquity, the quantum tori work just fine. Okay. But if you start adding more structure, which is what this slide does mention, and you really want convergence of the spectral triples, then I do not currently know, and it's not obvious. I talked to some people how to approximate the usual spectral triple with this method. You get an approximation of something that's twisted in an intriguing way.
Mm-hmm.
So that would be an example of which I wouldn't say I know it doesn't converge, but I would say it bothers me because I don't know how to prove it converge. If it does at all, I don't have a good idea of what the finite dimensional bits would be, but it's not going to be, well, it hasn't been natural so far.
By the way, Frédéric, let me ask you a linguistic question.
Sure.
How did you come up with the word propinquity? Because even educated native speakers have no idea what this word means.
Well, I've been living in the US for a while, but okay, so here's the problem. If you recall a couple of slides ago, I mentioned that there was a whole history of variance, right? So it started with Marx, who naturally called his metric the quantum Gromov-Hausdorff distance. Okay.
Yeah.
But then people started to have the non-commutative Gromov-Hausdorff distance, the quantized Gromov-Hausdorff distance, etc., etc. So every word sort of started to be taken. And eventually, around 2010-11, Mark did encounter, when he was working with modules, the question of what he needed the Leibniz property, which had been completely sort of ignored in all of these variants. And so he wrote a paper and he said, well, I would like all my quantum compact metric spaces to have this additional extra property. But if I do that, and we will see when I describe the Gromov-Hausdorff distance why, things break down and I don't have the triangle inequality anymore. So it's not a metric. So I don't know. And that thing that was not quite a metric, Mark called it a proximity because,
Ah, right.
And then at a loss for words, I ended up having to decide. I'm betraying the next thing here. I touched my screen. I chose a synonym for the word proximity because I was running out of words. And it turns out the word propinquity, which, by the way, if I had to translate it in French, would end up being the same word as proximity, basically, came to me. So at least I figured it would be memorable enough. And I was pretty sure nobody had used it yet. We will see other words today, Piotr, for your pleasure. Different.
Yeah. No, it's quite a lot of fun. I remember that we had some problems how to translate into French
Yes.
because we were the note in comprendit, entwining
Yes.
structure.
Yes.
But with the help of a native French speaker mathematician in Oxford, and she told us structure enlacée. So now,
that's nice.
if you ever wonder how to say entwining structures in French, it's structure enlacée.
Yep.
But propinquity is a wonderful word. That's the beauty of the English language. We have so many words.
Yes, it is a large vocabulary. So when, if that's okay, when you return to spectral triples. So spectral triples, remember, sort of where the origin a bit of that. But not all metrics have to come from spectral triples at all. It's just that these are maybe the examples that tend to receive more attention for obvious reasons. There's a closest analog of an actual Riemannian object, if you want, manifold. And so I actually did, after a while, I mean, there's a lot of steps in between, okay, I mean, a lot of history that I skipped, but eventually, applying some of my construction, I was able to specialize the propinquity to a new distance, but between spectral triples, which is 0 when the spectral triples are unitarily equivalent. So much more information is preserved than just the metric. And again, there's examples, some may be repetitive, but matrix models, that's what I was mentioning to the question. There are matrix models from physics. I picked actually a paper from mathematical physics. I don't know what physicists think about it, but these are actual physics models, and you could make them converge to the quantum tori. And they had a very natural finite spectral triple, but the limiting one is complicated. I mean, not horrible. You can write it down. It's not like that, but it is not the usual one. So that was interesting. Approximation of spectral triples on fractals, certain fractals. That was my work with Thérèse and Michel in advances. Collapse in Noncommutative geometry. Carla is among the audience, where this is a whole industry in geometry. We can prove some result there. Also with Carla and Judy, we have a full characterization actually of convergence of inductive limits. It is rare. Related to the question I had earlier, because of the nature of the Gromov-Hausdorff distance, it is extremely difficult to find necessary I mean, let me not say something too strong here, but it's an infimum of something. So finding lower bounds is hard. So finding things that don't converge can be hard because of this infimum construction. But here we have a full characterization of conversion, if and only if based on some algebraic structure. That's rare and nice. And then you can get some nice results, for instance, some sort of semi-continuity of group of isometries. And what's interesting and maybe really excited me, and in fact, I'm working on that right now, it's funny, is that when you converge with the spectral propinquity, we don't just have examples, we have more, we have consequences. And the big consequence is a form of continuity of the spectrum of the spectral triple, which you don't need to compute to prove convergence, but then you get as a byproduct, among other things, convergence of things like spectrum and even more. So this worked well. So this is the context in which today's talk takes place. But I wanted to give you...
Sorry, I have a few questions, in fact, if I could, sorry.
Absolutely, yeah,
sure. So first of all, I didn't catch what does it mean, this collapse in differential geometry. So could you please repeat?
Yeah, so you have imagine a manifold with a metric, and you make your metric vary, but so you get a sequence of metric spaces that do converge in the Gromov-Hausdorff topology to something. But that something is not the original manifold. It's some sort of quotient. Well, it's a manifold, but of lower dimension. You lost some dimension. That's what they call collapse. And they're very interested in this because basically, if I had to put that into the most general framework, I would say there is an interest in if manifolds converge to something, what can you say about the something? So, well, it's hard. But one thing you can do is assume that the something at the end is still a manifold. Okay, you don't know what, but it's still at least a manifold. And in that case, the only thing that can happen, the dimension can collapse. You could even converge to a point, but at least you can grow the dimension. You can reduce it. So there is a lot of study on that. It turns out I'm not a geometer, so what I'm going to say is a simplification, but that in some sense the manifolds that do converge. So suppose you have a fixed manifold m blah blah blah, just varies a metric, and then poof, at the end it becomes some manifold n with some metric. Because what did you do? Well, in some sense, your original manifold is sort of some sort of vibration or some, but this is a technical term I should not employ because the actual structure is more complicated. But it has some sort of structure, a bit like a sort of complicated bundle over the collapsed one, and you're basically shrinking the fibers. So what we did with Carla is we did a sort of simple example like that. Like think of a cross product where you shrink the fibers that go along the group the orbits, if you want, and you can reduce yourself to the base space metric, things like that.
Okay, thank you very much. One more question is about this semi-continuity of groups of isometry. So what vary in this example?
Yes, so if you have a converging sequence in the sense of the spectral propinquity of spectral triples, they can be on all sort of algebras and everything, just a converging sequence.
Okay, I see.
You see what I mean? Then you can look at there are actually two groups of isometry. I learned that from Roberto, and maybe there's more, but at least two. One is actually isometry for the metrics, and one is isometry implemented spatially by unitary. And you can look at those groups and you can ask, well, what can I say about the group at the limit? And we can say stuff. There's result on group for AF algebra. There is a whole article. It's pretty. There are some nice results, which to a large degree extend some of the things that we knew in the commutative case, but to, I don't know, like simple AF algebras, for instance, things like that.
Okay, thank you very much. And one last question about this continuity of spectra. Is the spectrum of Dirac or the dimension spectrum of
the spectral of Dirac, the eigenvalues of the Dirac.
Okay. Thank you.
Including their multiplicity. In fact, I just realized recently that I could slightly improve the paper in Math and Ellen where this is proven. I will apply this. I hate to do this, so please don't steal it. I need 2 more days to put it on the archive. I usually don't talk about papers I haven't published, but under one of the conditions that geometers look at, where there varies a metric, there are all sorts of topologies you can put. If you put one of the topologies I care about in differential geometry, you could ask, are the eigenvalues of the associated Dirac operators, assuming it's spin manifold, etc., varying continuously with respect to the metric within given topology, and I can reprove that what they have in geometry using my techniques, taking a different path. And what's interesting about that is, again, maybe I'll give another talk on that, but there is something in the way they do it that makes me a tiny bit uncomfortable. So I'm actually quite happy to be able to do it my own way and bypassing some of these difficulties. So you can recover stuff. And the reason I do this is because it would be interesting to me to say, well, if I can do what geometers do, now I want to do more, right? I want to look at what happens when the limit is more singular, not with geometers. So it still makes sense to talk about spectral triples sometimes, even if you don't have a Riemannian manifold at the limit. And then this sort of result might extend.
And also, I'm a little bit worried about this collapse in differential geometry together with this continuity of spectra. If you have collapse, your dimension drops. So would the spectrum still be continuous?
So some of the eigenvalues go like, so I did not write to you what continuity means. It's a sort of Hausdorff convergence. If some eigenvalues disappear to infinity, you just lose them. So it works just fine.
Yeah, so since this asymptotic behavior is somehow encoded in the spectrum of Dirac, yes?
That's right.
But it somehow does not contradict anything, yes?
That's right. That's right. Okay. So you have to make the definition of what converge means precise, which I'm not. But it is essentially a Hausdorff convergence of the spectrum, if I had to describe it. So you can see that some eigenvalues could disappear at infinity. So that they just go away. Some could collapse to 0, all sort of things. If you look at the paper with Caroline and I, which is on the archive, right? It's one of my recent ones. It's called Collapse. I think I just called it that. It's still pretty appropriate to my state of life right now. If you look at this paper, you will see that we can collapse to a point, and it doesn't contradict the continuity. But you have to look at what happened there.
Okay, thank you. Thank you very much.
Sure. So, okay, all of what I've said is about compact quantum metric spaces. What about locally compact metric spaces? I mean, remove the unit of the sister algebra proof, you have something locally compact. And it turns out it's a red box because this has been much, much more elusive. And none of what I've said is relevant to it. None. And you could ask yourself why, and it hasn't been explored really much. I mean, there are two papers plus epsilon, and the 2 papers before the epsilon are mine. The epsilon is someone using one of mine to get an example, so that's great. But it's really not much explored. And so you might wonder why. And it's really because basically what happens is the picture that you had in the compact case, as we shall see in the next 2 slides or 3 slides, simply completely collapses from the root. That is a Monge-Contreras metric that Mark mentioned in a quote earlier, does not behave well. So what you used as your prototype simply dies completely when you go to the locally compact case. So we have to do something which complicates life, and this is what I will talk about today. Because as my goal, I in fact want today to exactly do that, tell you what a locally compact metric space is. More specifically, as the title suggests, proper ones. So what's a proper metric space? It's a terminology. It's also called a boundedly compact metric space. And as the name suggests, it means that closed balls are compact. So, Rn. Okay. So it's a stronger notion. I will define locally compact, but these are the one that you want to work with when you do Gromov-Hausdorff convergence anyways. And today I will not only tell you what a proper quantum metric space is, but what would be a generalization of the Gromov-Hausdorff convergence to them. And it's all in this preprint listed here. Okay, so let's start. So I'm going to do the usual. I'm going to tell you the classical picture and then generalize it. It's easier that way. And it's nice with metric spaces because it's very, very straightforward. So you take a metric space, locally compact. In fact, you could put, I think I put in almost all size separable in front. I'm not going to care too much about anything else. And for any function, you can define the Lipschitz semi-norm that everybody knows. But okay, that's a semi-norm on the space of functions, so that's the right sort of thing to discuss non-Kerr geometry, right? Something that lives at the level of functions. So what makes Lipschitz semi-norm special? Among all possible semi-norms you could put on the sister algebra of, say, continuous function on x vanishing at infinity. Well, I'm going to tell you, I'm going to give you a little hint. What's nice about Lipschitz semi-norm is that based on the observation of Mark and before that Alain Cohn, we can define metrics on the state space between states using this. So there are, in fact, many. And I'm going to define a family of metric. Here you go. So sometimes this is called the bounded Lipschitz metric, which is why my macro still uses BL. But I discovered along the way that, in fact, it is due to Forte and Mourier in a paper in 1953. So I will probably keep oscillating, calling it Forte-Mourier distance and bounded Lipschitz due to bad habits. And there is this parameter M, which is a real number. I didn't write that anywhere. I apologize. Think of M as 1 or more. It doesn't matter. We want M to be big, but the default would be M equals 1. And this is a uniform distance between the states taken over a ball for a norm. And that norm is the max of the Lipschitz semi-norm and the usual norm, or if you want your M here, 1 over M times the usual norm. It doesn't matter. For now, it doesn't matter.
Sorry, Frederic, I have a dumb question. Can you have a metric space that is not locally compact?
Can I do it? No. At the moment, no. No.
But
because at the moment,
that every metric space is automatically locally compact?
Oh, no, it's not the case. No.
So what would be an example of?
Oh, sure, the unit ball of L2.
Yes, the dimension goes. Okay, thank you. This is what I would need it. Okay, thank you. Mm-hmm.
No problem. No. So because I work on sister algebras, the topological nature of my object is local compact. I mean, sure, they're non-commutative, so there's no space to speak of, but the Gelfand duality tells me that if ever my basis algebra was commutative, then the spectrum would automatically be locally compact. So I am in that realm. But when I'm going to do Gromov-Hausdorff distance, locally compact is still too large because you want at least complete. I mean, again, I'm going ahead of myself, and it's good I have 90 minutes. But if you have spaces and you take the subset of a metric space, and you take the Hausdorff distance between them, if you want that to be actually a distance, you're working on closed subsets, right? Because otherwise you can have the Hausdorff distance between open interval 0,1 and closed interval 0,1 is 0 in R. So you have some extra conditions. So what's closed? Well, when you work in the world of compact metric space, you don't ask the question because that's fine. It's compact does the trick. But in locally compact, you need something, and it's the form of completeness that you need. And the right notion of completeness that you need is not just complete, it's not enough. It's proper, which is the thing I indicated. I believe Thomas has a little hand. You're very lucky I saw it because I never look. Yeah, go ahead.
My question is about the role of this constant M.
Yep.
Why do
what is the question?
For Ted-Mourier, why do they need this constant
They don't.
M?
I do. They don't. For Ted-Mourier, just put M equals 1. Okay. So what happens if you change M? Well, all these metrics are equivalent. It's trivial. So topologically, it doesn't matter. But metrically, it does.
Okay.
And I will explain to you why in a few slides. It will become apparent. However, until many slides in the future, it doesn't usually matter until then. Then there will a point where it will become very clear why it matters, but it's going to take a little while. So if at first you want to assume M is 1, you're not going to lose much to the talk, but eventually it will be convenient for my work to have this M. Basically, because you truncate the metric to M. That's what happens. So if you have a space that's huge, you're just looking at it. You're just not looking with the original metric, but the metric truncated at M. If I had to give you a heuristic. Yeah.
So if you have a family of such spaces, do you assume that this M is uniformly bounded, or
I'll explain
what
to
is happening?
Keep that question in mind,
families?
and I will answer that question.
Thank you. Okay.
Yeah, no problem. It's just literally like if I do it now, I have to jump 20 slides. So that's exactly the question. What do we do with this M? What sort of uniformity you want? So keep that in mind. But for now, don't worry too much about it. If you want M to be 1 for the next 40 minutes, that's cool. So it only becomes an issue later. And then there's another metric. So this is a very good question. Keep it in mind because it's very relevant, but it needs some explanation to be addressed. The Monge-Korteweg metric is not a metric in general, in spite of its name, but it is defined again as a supremum distance of difference between states, but over the unit both for the Lipschitz semi-norm. This can be infinite, even between two states, actual state, not just infinite radius. I'm talking two states could be at infinite distance. So keep that in mind, but it's still called a metric. It's just the way it is. So they're very similar, right? And the one I mentioned in the introduction is that second one. In the compact world, that's what people use. Obviously, I'm introducing the other one because this is what we are going to use. But anyway, so let me talk a little bit about this metrics, okay? In the classical picture first. So first, let's look at what topology do this metric induce. And both of them are defined on the state space. And I will make the executive decision that the right topology on the state space is the weak star topology. So I would like them to induce a weak star topology. So and there are many good reasons for that, but let's start with that. So it turns out that this is anyway automatic. This just happens for free with a Forte-Moyer metric. That's what it does. It metrizes the weak star topology. And if your space is nice, to address the question I had a few minutes ago, you see what happens with the M here? It truncates. You can recover the original metric up to this truncation with that M. So if you want the actual metric, well, you would like M to be really big, right? I mean, possibly infinite, which is the problem, because if M is infinite, you exactly get the contour of each metric. But other than that, this is the story. So the Forte-Moyer metric is well behaved. It induces a weak star topology on the state space for free, no matter what. As long as your space is locally compact separable metric space, it works. So it's a good foundation, and it's not a new observation, unfortunately. It's an observation I made when I was a new mathematician. So that's funny. And I proved long ago, it's part of my dissertation actually, so that in fact I know exactly when that happens in the non-commutative setup. So you give me a C-star algebra, you give me a semi-norm L defined on a dense subalgebra, because typically not every function is Lipschitz, so you have to account for that. Same in the non-commutative. A doesn't have to be commutative anymore. L is whatever it wants to be, as long as it's a semi-norm and it's densely defined. And I wrote dense subalgebra, but that's because of where we're going. I should have written subspace. You don't need an algebra for that. It's long ago. Then you can define a Forte-Moyer metric, and just to annoy you, here I chose arbitrarily M to be 1, because that's how I wrote the paper, I think, at the time. It's been a while. But anyway, so this is a metric with M is 1. Doesn't matter. As I said, they're equivalent. So take whatever you want. This metrizes the weak star topology if and only if you can find a strictly positive self-adjoint element. Strictly positive means when you apply a state to phi, it's always not 0. Well, positive, because I want it to positive. Strictly positive. So there exists such a thing, such that if you take that ball of elements upon which you take the supremum, the bounded Lipschitz metric is a uniform distance over some space. Well, you take that space, so the A, which have Lipschitz norm and norm less than 1, and you kind of, I don't know how to call this, but you sort of truncate them or whatever. You multiply left and right by age. This has to be totally bounded. So this is a very nice full-on comparative. This is an if and only if. And it recovered at the time, which is a long time ago, a theorem from 98 of Mark from that paper I quoted. But in the case where A is unitole, in which case, of course, you can choose H equals 1. But if this is the right form, and this pattern, we will see it again and again in this talk. So keep it in mind. So this is a nice metric, right? It metrizes the weak star topology for free in classical picture. In non-classical picture, we know when it does. We have a good criterion, and it's natural. It has to do with total boundedness of the Lipschitz functions in the appropriate metric, or if you want, or norm. Those of you who are interested may say, hey, is that the strict topology? It isn't. If I had written HA, comma AH, then it would have been. But it is a weaker topology than strict topology. That is interesting and intriguing. Anyway, okay, what about Morse-Kantorovich? And again, please interrupt me if you have questions. I don't mind. I can speak all morning. You probably will get bored, but interrupt because I may miss the little hand. So the Morse-Kantorovich metric, on the other hand, well, it does give you a topology that's finer in the classical picture, but usually it's not the weak star topology. Usually it's not even a metric. I mean, it does have a triangular equality. It makes sense to talk about topology, but whatever sense you like. There are two different natural approaches. They will agree, but you will have these islands of states which are at infinite distance from each other. It's a mess. In general,
May I have a question?
Please go ahead.
So it is possible that some states are in infinite distance with respect to this Morse-Kantorovich, but you can define a relation. I presume that it would be an equivalence relation.
That's right.
Two states would be equivalent if their distance is finite. And would you get something interesting if you take a quotient of the space?
Not
like
usually. I mean, these pieces don't talk to each other, right? I mean, it's like disconnected pieces, if you want. But what's going to happen? Well, that's it. So on each piece, no, you still don't metrize a weak star topology or anything like that.
Mm-hmm.
It's still a nasty topology on each piece. Okay,
but I'm not asking about particular pieces. I'm asking about the quotient space.
No, because no, I mean, so you're taking the quotient for the sequence relation, just roughly. Yeah, I don't know exactly what you get. It's a mess. I mean, because like what happens is basically if you have a point, okay, so a character of the algebra, just a pure state, to be an infinite thing, like I don't know, the Cauchy distribution will be at infinite distance from any pure state. Right? I mean, it's a matter of, you see what I mean? Like, it's a matter of how much it spreads compared to the other guy. And in non-code geometry, it's even worse. So it seems to me, it's an interesting question, but I don't have a good answer to give you. I think it's nasty because it has to do with, I mean, under what condition are they at infinite distance? Well, it's kind of tricky to kind of guess, if you see what I mean. If you look at my paper in 2012, I will mention in a moment, I have examples of state at infinite distance on the compact and they're kind of like different pure states. I mean, but they're still at infinite distance. I mean, it can be very nasty. So, I mean, I'm not saying it's uninteresting, but it's not, I don't have a good answer to that.
Okay, but still you would get very many components, yes?
You could. Depends on the space. I mean, if the space has infinite radius, yeah, you could get very many. Yes. Okay, you could get a ton. I mean, in my example, in the compact, okay, this is literally 13 years old, but the way I remember it is you take your algebra of compact operators and I build some metric which has some properties that are nice, and then what happens, which looks like a converged metric, and then what happens is it's well at, you know, when you construct it, you pick the basis of the Hilbert space. You have K acting on L2 of something, you pick say a canonical basis L2 of N, and you made a metric out of that. Then you take a completely different Hilbert basis and you will find some state at infinite distance for any, you know, really any completely not. So it's pretty messy. So that never became a major focus of mine. I was more trying to look at the regular rather than irregular aspect. And the regular aspect is due to the main theorem I know is due to Dobrushin. If you ask yourself, why is this Monge-Converged metric not called the Wasserstein metric? Well, it is. It has many names. It is historically correct that it is due to Kantorovich, 1940. And then the formulation I gave you is due to Kantorovich and Rubinstein, 1958. Wasserstein wrote his paper with the SAD metric, among others, in 1969. Dobrushin, right after that, named that metric Wasserstein metric. That's a probabilistic universe versus the transport universe. And it has other names on top of it. In fractals, I think they call it the Hutchinson metric. I mean, whatever. But we will try to be historical. So Dobrushin proved that if you have a separate locally compact metric space X, a substate, the weak star topology is metrized on certain subsets of the state space. And this is, we're not going to do much with this. I just wanted to give you that for culture. This is a condition that Dobrushin has. It's a sort of strong form of tightness. You want uniform convergence on your set S, not of just the weight of all these measures outside of a large ball, but actually the weight of the integral of the distance outside of the large ball to go to zero. So it's stronger than just being uniformly tight. It's not even enough that S is weak star compact. It's more complicated than that. But here it is. Here you have a sufficient condition to know what sort of subset of state space are metrized more or less correctly by this Monge-Converged metric. And if the space is compact, you can see this condition is automatically met. And as such, we recover the fact that in that case, in the compact case, yes, you do have weak star topology on the state space induced by the Monge-Converged metric. And as a bonus, you recover the metric altogether. And this corollary, well, you can prove this directly. You don't need to go through Dobrushin. It just makes the flow of the talk nice. But this corollary is the foundation of essentially Mark's idea. Okay, you take the Contorovich metric from an abstract semi-norm and you ask it to metrize the weak star topology because it behaves well when the space is compact. But when the space is not compact, this is not great. All right, so why did I keep this? I have no idea why I kept Dobrushin theorem, but I did. Oh, no, I know, I remember, sorry. So you could ask, and I'm not going to make a story about it, so I will maybe skip questions about this slide and leave it for the end because that's not important, but I just included because, you know, there is a history to this. You could ask, can I mimic this? Can I invent a condition that's similar to Dobrushin and ask what should I L satisfy on a non-commutative algebra so that this thing that would reduce or at least be similar to Dobrushin would somehow work even in the non-commutative setup. And there is a theorem that I just mentioned, the paper from which it is. And it can see the same pattern emerge of the bounded Lipschitz condition that I talked to you about recently. That is, things will work. The Monge-Converged metric will be well behaved in a way that I'm not going to define because I don't need it today, interestingly. If there is a strictly positive element that the right thing is totally bounded, and it's still of the form H for A of Lipschitz norm less than 1, but A is now in the unitalization of A, and it must kill some state. So it's a slightly different set, but it is very similar condition. And the reason I put it here is because we will see a milder version of that in my definition of a locally compact metric space. But I will not need to define to you what a dense subset of states is, which is nice. Just know that it is a non-commutative version of what Dobrushin had noticed for us. That's still in the theorem on the slide. So there's things you can do, but you have to make a choice. Now you have two metrics. Which one do you pick? How do you make a definition? Okay, so for me to justify a definition, one more tiny observation related to what I said before. Yes, in general, you have islands. As we say, the distance could be infinite between two states, but the Morse counter-H metric does have a little regularity. There exists a state, in fact, any character would do, any pure state would do. But there exists a state such that if you look at every state that is at finite Morse counter-H metric from it, that's weak star dense. So yeah, some of them are far, but a lot of them are not. And it turns out that in keeping with the previous slide, if you look at this set, H, F, H, where H is strictly positive, again, for functions on the utilization with Lipschitz semi-norm less than 1 and say vanishing somewhere, then this condition, this proposition is a corollary of asking for such a set to be bounded. I'm going to take it here. So we don't need totally bounded, but we will keep the boundedness of a set like that because it gives us this weak star density, which is quite helpful. Yes, Tomasz.
Could you come back to the condition in the Dobrushin theorem?
Yep.
One slide before.
So
yes,
that's the same. It's up there.
So,
yeah.
So I'm reading this integral as some average distance from x to some distribution around this x outside some ball.
Yeah,
okay?
Essentially.
So I'm, but the geometric meaning of this condition is still elusive to me.
No, it's a behavior at infinity.
Kind of,
so sorry, I didn't mean to interrupt. There's
I'm looking at this and I'm seeing some kind of concentration of this distribution, probability distribution around this x.
Yeah. So okay, the x doesn't matter. The x is just a reference point. If you change the x to another x, the condition is the same. The thing that matters, yes, they are an expected value of random variables if you want to look at it this way, but the random variable is a distance from some point, whatever you want, to the variable. Now, this is really controlling the behavior at infinity. I mean, the simplest way to understand what happens is if all the mu's are supported on the compact, this is automatically true. So what happens now is you want your probability to maybe spread over the space beyond the compact. Okay, but do so with enough, not so little weight when you go to infinity that this integral will still go to 0 uniformly. So it is a concentration. I don't know if you're familiar with that in probability theory. There is a concept of uniform tightness, which is a characterization of weak star pre-compact subset. It's very important in probability theory when you do convergence result. And the idea is like this. For any epsilon, you can find a compact so that your entire family of probability under consideration gives that compact mass 1 minus epsilon. So basically, it's almost entirely supported there. And if you can do that, then that's if and only if the space of probability is weak star compact, pre-compact. And I used to be a probabilist, 25 years ago. So I remember this is important. Well, this is a stronger version of it. It's the same idea, except you don't want to just to be 1 minus epsilon on the compact. You want that on the compact, when you integrate the distance, which could be huge, you still essentially almost 0. Does that make sense? So it's supported very tightly.
Yes, I have some difficulty because I'm trying to reading this as a condition of vanishing of this probability distribution at infinity.
Essential, but vanishing in the sense of this distance. That is, just vanishing is not enough. Okay, Cauchy sequence is an example. The Cauchy distribution is not even L1. Okay, so if you integrate X, which is not the distance on R, but okay, it's the absolute value of X, against the Cauchy distribution, poof, it's infinite. So that's already bad. So you want things to kind of like smooth out at infinity fast enough that if you integrate any one Lipschitz function, you get an actual finite number. And there's a uniformity in the process. So maybe if you have a density, if you have a density for your probability, the density decays faster than the distance.
Okay. Okay, thank you. Okay.
I don't know if it helps, but that's the way I would look at it. Okay, so after all of this, let me tell you what a locally compact metric space is. It's high time. I get there. So the 2.0 is because this paper in 2012, I proposed my first definition, and then I actually refined it in a never published preprint. It's on the archive, but it didn't work. I mean, I put it there because I suffered on that in 2014, but I wasn't satisfied, which was my first attempt at what I am talking about today. So there's been a sort of pre-version that nobody really cared about, so it doesn't matter. But, you know, to be historically accurate, this version I'm going to propose to you today adds some things, namely Leibniz property, which I didn't care about before I did the work on the propinquity, like anybody else. Now I do very much. So it adds some conditions, but from a topological standpoint, it actually is weaker than what I asked before. So it's kind of easier to get examples, I think. Anyhow, here's the idea. So a quantum locally compact metric space is going to be a structure that mimic some of the properties I have discussed for the last many minutes. So first, it's a pair of a C-star algebra, which is no longer required to be unital, but is separable. And a and a seminorm L, which is going to be my analog of a Lipschitz seminorm, but it's just a seminorm. And so there is a lot of words, but I'm just define them verbally because they're easy. So L is what I call, first of all, a norm modulo constant. What does that mean? Well, I mean, if there is, it's just a term I made up, but if there is a unit in A, then you want L to be 0 on that and all the multiple of that automatically. And that's it. It's only 0 on the multiple of the unit. If there is no unit in A, then it's a norm. Okay. This is just because I don't want to write on the slide 2 cases and so on, but this is just that. Because the Lipschitz seminorm is actually a norm on C0 of X if X is actually not compact, interestingly enough. Hermitian just means L of A star equals L of A. I don't know how to call that. So I want that to be defined on the dense star subalgebra. This time I do want a subalgebra. So, okay, so that's, the Lipschitz seminorm does that. I mean, Lipschitz function form a dense subalgebra of C0 of X. And then I introduce a Forte-Moyer metric, which I already did in this non-commutative setting. Okay, here it is. Now I'm going to use sometimes this notation in the paper. Sorry, in the paper I use that a lot because it's, you don't want to drag. So I introduce this Sobolev-like norm or Lipschitz norm. I don't know how to call it. It's not really Sobolev, but kind of, which is a max of the norm in the Lipschitz seminorm. So this is what this subscript L means. And so, that's the thing we've seen before. And I want that to metrize a weak star topology. And if you recall, we have a characterization of that. So that's good. And we know it's always true in the classical picture. I want the Leibniz property. I keep saying the name. Now, here is the actual formula. This is a technicality. I keep saying that in every single one of my talks because we have the same technicality in the compact. You could remove that and make the theory uglier, but you would not gain a single example. So we put that. There's a way, if it's not true, to make a new Lipschitz seminorm that has all the same properties, gives you the same metric, but has this extra bits. And then this 0.5 is ugly, but I told you the preprint has been online a week ago. But it is exactly what I talked about 5 minutes ago. And that is to guarantee that we have a state mu, so that if you look at all the state at finite Monch-Kantorovich distance from mu, it's weak star dense. Except I want a tiny bit more than this. This is a condition that works, which I just told you a minute ago implies this. So what you want is the existence of this H, so that if you look at everything of one Lipschitz, Lipschitz seminorm at most 1 vanishing at that mu, then this set is bounded. And again, it's saying that you can, sort of smooth things out, that if your Lipschitz, your growth is controlled. So if you are 0 somewhere, you can only grow so far. And so you can find an element that would actually kill everything at once. That's a boundedness, so that things don't explode to infinity. But that's it. That's my proposal. So if you're familiar with the compact definition, which I will allude to so shortly, this should be familiar because this is similar. All right. So first example, yes, classical picture works. Okay, that's obvious. We modeled it after. Second example, if you don't know what it is, well, now you do, because the quantum compact metric space is an example of that structure. Okay, and it's better than that. And that theorem will help you. In fact, a quantum compact metric space is just exactly an example of what I just showed you, with A being unital. So all that theory that I've been working on, Mark has been working on, and other people, Kat has written paper. I know I mispronounced his name. Mispronounced paper. I mean, a lot of people have wrote. I mean, not a million, but this is something people have worked on. It all fits perfectly fine. We haven't destroyed anything. We just added the non-unital case. Okay, so that's that. Oh, by the way, in that case, H is 1. Okay, and I'll just say that for the expert, so to speak, because this is a bounded Lipschitz, and because of that M, which here is 1, because of that M thing that we alluded to, automatically the radius or the diameter of the state space for this metric is always, well, here at most 1. Obvious. It's trivial. So, okay, in the compact situation, you want the Monge counter of H, not the bounded whatever. You want the Monge counter H metric to give finite diameter to the state space. So that's why you need condition 5. It turns it's basically one of the reasons to guarantee that everything works. But it serves a purpose in the locally compact case too, as I mentioned. Okay, so that's cool. Here's another example I put earlier. Now I understand you're gonna tell me, oh, but I want some really fancy, sexy example, and I understand that. So do I, and I have plenty on my to-do list, and it will come. But these are after 85 pages. I decided I would stop that preprint. So here is a truly non-commutative, non-unital example, as simple as possible, so that we can digest it. Okay, I almost wanted something easy. So first, this first example is trivial. I need it for the next slide. So look at C0 of Z. So that's just Z as a metric space. You can define a Lipschitz seminorm the obvious way, I mean, the usual Lipschitz seminorm, which would be evaluated a function at n+1 minus the function at n. It takes the soup of that over all n's, but you can implement it as a commutator of it's fun, right? Because we like spectral triples. You can implement it as a commutator with a bounded operator. So it's a very simple Lipschitz seminorm. And yes, I know U is a unitary, not a self-adjoint thing, so it's not a spectral triple in that sense, but it looks like one, so that will do. So I'm just putting the usual metric on Z, okay? And it fits well, and here is L. Why did I write my L in this weird, funny way? Because then what you can do, which is more interesting, is you can make Z act on itself by translation. It doesn't have to be Z acting by translation by 1, Z acting by translation, adding 5 it doesn't matter. So then you have to do something with this part of the cross product. We know how to metrize C0 of Z. What about the Z acting? Well, we also know how to do that. I mean, it's standard. You define a derivation along this way. It's in the Fourier picture, right? So it's just multiplication by n. And you make a sort of Dirac operator by adding those two with gamma matrices. I didn't even write what gammas are, but the usual, your favorite choice of gamma matrices, and a representation of the Clifford algebra on C2, whatever. And okay, this is an example of a quantum locally compact metric space, this cross product. And this cross product, of course, if the action is literally action +1, which is just Z acting on itself, the obvious way, this is a compact. And well, okay, on the one hand, sure, you could criticize me for starting with a compact, but it is certainly non-unital, and it's certainly non-commutative. It's simple. So this is in that sense, it's a non-trivial example of our animal that is completely not fitting. There are others, by the way. If you're curious, the Moyal plane, which unfortunately is also the compact, fits well. There are other things. But this is the one I want to talk about because that's the one I put in this particular preprint. So we have examples. Classical examples we've already known and new ones. Okay. No question. Perfect. So, oh, and this example is really nice, by the way. We'll get back to it, I hope, at the end. And it's really nice because this construction is, I chose it for this reason. So maybe, I don't know if it's a good or bad marketing ploy. I can't tell you that. But I think it's good, but I could be wrong because this is a cross product, right? And if you have a cross product by isometries for some Dirac spectral triple, we know how to make a spectral triple on the cross product. And this is it. This is what you would do in the classical, the situation where your Bayes algebra is unital. You would do something like this. And it works just fine in the non-unital case now. We have the bounded Lipschitz metric gives you the weak star topology. All that stuff works just fine. So that's, that's nice. I mean, because in a way, it is reassuringly comfortable, yet is absolutely new. And we could not have handled this, 2 months ago. So, okay. So in order for me to move forward, I need to explain to you, I will return to the Gromov-Hausdorff distance with nice formal definitions. But before I do that, I still have to talk a little bit more about what a locally compact metric space is. So I'm going to make a picture because I need justification for some of the definitions. So where am I going with this? I am going to define a form of convergence for a subclass of the object I introduced. How do we define convergence of normal classical proper metric spaces? That is, metric spaces that may not be compact, but their closed balls are. Well, this is what Gromov suggested in 1981. This is actually the real Gromov-Hausdorff distance, by the way, in opposition to the compact one, which was introduced earlier. This is actually what Gromov introduced. It's a locally compact situation. So I did a ball and a plane. Why not? And this is a bad embedding, but it's also easier to draw. So you have the ball of radius r. Okay, that's one space. It's compact. And then you have the plane. And you want to say, as the ball grows bigger and bigger and bigger, looks more and more like a plane. Okay. You may or not agree, but actually it's true for the Gromov-Hausdorff distance. Okay. And the way you do this is that you're like, well, obviously, if you just take the Hausdorff distance, you embed the ball and the plane into 3D space, I just did, and you take the Hausdorff distance between them, it's bad, because it's automatically infinite. So that's not going to work. So what you need to do, if you want something interesting, if you want to be able to approximate locally compact spaces by compact, let alone, say, finite ones, you need to be local. You need to say, well, I'd be happy if I can find a radius. This is my radius r here. So this, the picture is, let's see, I have a pen somewhere. This, ooh, what just happened to me? This here, I need to put it in this mode. This here, you see this little cap here at the bottom, this little piece of sphere. That's actually the ball inside the sphere of radius r, center x0. Okay, that's this little cap. And that should be close to the plane. And the ball of center y0 and radius r should somehow be close to the sphere. And you want r to be as big as possible, and the distance between these two balls and the other space on the other side to be as small as possible. That's the idea. So you're trying to make as big a ball as possible close to the other space, and you do that, from one space to the other symmetrically. So that's the idea. Of course, that would be a terrible way to do it, right? I mean, you would put the sphere should be sitting inside the plane somewhere, but it doesn't matter. Then the picture is unreadable. And for that to work, I need this reference x0 and y0 point. What are those? Well, they completely, you choose them. They're base points. So the Gromov distance is not defined between metric spaces. It's actually defined between pointed metric spaces. You chose a base point, and then you sort of exhaust the space around those base points. So we need to talk about choosing a base point in non-Cohen geometry, right? And what's important about the base point is not the point itself that much. It's that it allows me to slice my space into ever larger chunks using, in this case, balls. That's a natural thing to do in a classical picture. Obviously, we'll have to be a bit imaginative in the non-commutative picture, but I'll explain that. So we need not only base points, but it's not enough. What we really want is a way to exhaust our space into some sort of subsets that are ever larger. Does that make any sense?
I guess so.
Okay, well, we'll see. Well, luckily, you'll have a formal definition shortly. So let's start with an easy idea. What could be a pointed quantum locally compact metric space? Well, it's a C-star algebra, Lipschitz semi-norm, I told you that. And then you pick a state. Done. That's your base point. Yes, you want your state to have the nice property that everything, there's a weak star dense subset of thing within a finite Monge converged distance. Otherwise, it's going to be, you're just going to talk about an island. But it always exists. That's this condition 5 guarantees that we can find such a state. In fact, many, but we can find one. I call that a pin. Imagine on a map putting a pin. Now, it's not a point yet. Okay. So that's just a definition. A pin space is obviously a triple where you have the thing I described before plus a state. Okay, fine, whatever. So with that in mind, we could be happy. You could say we're done, but no, it's a little bit more complicated. Now I'm going to tell you something really interesting for the work I've done. Maybe to you, I don't know, but for me, it's very important. So take one of those, quantum compact metric space, and you pinned it. And say you have a sequence in it. Bear with me for 2 slides here. They have a sequence in it, and it satisfies the following 3 properties. Its norm converges to 1. Its Lipschitz norm converges to 0. And at this state, it's almost 1. It converges eventually to 1. So if you have a classical picture of this, it's a bunch of functions, which are of norm essentially 1, that are essentially valued 1 at some point that if mu is a character, which I don't assume it is, but for the picture in classical geometry, that would be the easy way to picture this. But they flatten, right? Because the Lipschitz semi-norm gets smaller and smaller and smaller. Suppose you have a sequence like this. Then I proved that it is automatically an approximate unit. Poof. That's pretty cool. So it's a metric condition to get an approximate unit. Now, before I knew that I'm very happy I have questions. It means what I'm saying makes some sense or makes no sense, but is interesting enough to worth digging in. So I actually included a proof. I'm totally going to skip this. All I'm going to say is basically you look at this magical pin state and you look at any other states, and well, by definition of Monge metric, you have an inequality like this, so that will converge to 0 as long as the Monge metric is finite, which happen. Sorry, that should be a mu, not a psi, a mu. But so you get that you sort of weak converge to 1 for states in that weak star dense subset. But then you use the fact that bounded Lipschitz metric metrizes a weak star topology. That's where it's important to say, well, then it's going to actually converge weakly to 1 for real, which is cool. Then you use a little bit of cat-descent functional calculus, invokes the enveloping C-star polynomial algebras, and after some work, it's an approximation. It works. Okay. There's no commutativity assumed. Everything is cool. I'm not going to do that. It's in the paper. I don't have time, and I'm happy I don't. But it's a nice theorem. So let's look back at the definition. When do I have such an approximate unit? I mean, these are nice. These are very intuitive. These are nice, and they're very useful. Why do I even bring them up? Well, precisely, I should have put the next theorem here. Because of this theorem, which, yes, I know I read it backward, but I kind of have to. Because among all locally compact metric spaces, XD, those that are proper, that is a closed ball are compact, they correspond exactly to those compact quantum metric spaces for which there exists such an approximate unit. That's a if and only if. And so I know what a proper quantum metric space should be. It's a locally compact metric space with such an approximation. That's it. And so that's cool because now I can do Gromov stuff because I have the right notion of locally compact Hausdorff space with the additional condition that closed balls are compact, which I need for Gromov, even classically. I mean, you can define the distance without that, but it's not a distance. It could be 0 when you don't want it to be. All right. So in addition to that, I will mention the theorem. It really should be a lemma, whatever. I was optimistic here. It's very easy. If you have a quantum locally compact metric space and there is an approximate unit which is bounded both Lipschitz and norm, then automatically the state space is complete. Yeah, because in locally compact spaces, completeness is not automatic, like in the compact case. So this is a sufficient condition for completeness. And you can see that a proper one, well, since it contains an approximate unit that is even better than this, it is in particular complete. We get back that a proper metric space is automatically complete, which is true in classical geometry, metric theory, but it's also true in the quantum case. And then there is another cool thing. This is fun. If you have a quantum compact metric space that is proper, either it's compact, that is, it has a unit, or it's not, but then its diameter must be infinite. And that, again, is the same thing as the classical theory. So this new object we introduce, this quantum proper metric spaces, behave in the non-coherent realm, at least at a naive level, just like their classical counterpart, and fully characterize them as a bonus. So that's a big.
Sorry, is it automatic that if your quantum metric space is compact, not only locally compact, then this diameter is finite, or
it's part of the definition? So yes.
Okay, it was part of the definition. Okay.
That's right, but I will tell you. But yes, it's still a good question because it's not obvious from this definition. It is obvious from the compact definition because it's pretty much stated. So in the compact definition, you would have the Kantorovich distance, not the FRÉDÉRIC. And we would ask it to metrize a weak star topology. Of course, in that case, it's a compact space, so it has finite diameter. In the FRÉDÉRIC picture, I lose this because, well, I mean, this is bounded by force. So you lose that information, but this 0.5 that catches it back. So yes, it is, but there is work. And this is this theorem that I mentioned, that if your unit and a quantum locally compact, you automatically compact, which implies in particular, yes, that the diameter is finite. That is correct. Yeah. You have to prove it, but it's not too bad. I mean, there are some nasty proofs in this, I would say. It's mostly built into work, I would say. But it is a proof. It is fair.
Okay, thank you.
Frédéric, could you please tell me again what is a classical property space?
Yes, it's a metric space where every closed ball is compact.
Okay.
It's also called boundedly compact, but it's longer. So I went with proper. It's an official terminology. I didn't make that one up. So any Euclidean space, any manifold, anything finite dimensional will do, for instance. But so I mean, clearly you need to be complete. I just mentioned that. So the open interval 0, 1 is locally compact, but it's not complete and certainly not proper because the ball of radius 1 is not compact, of center, whatever you want. And no ball of radius 1 is compact in the open interval 0, 1. That make sense?
Yeah, thank you. Yes.
And that is what you need. I mean, so I need it. I need it 100% for what I do. But it's not just me. If you take a book on metric space theory, you will see that the Gromov-Hausdorff distance being 0, implying the spaces are isometric, requires typically that at least one of them is proper. So it's just a natural setup. All right, let me give you one more definition and then go to my convergence. So remember the idea. Yes, I have a pin, but I don't really care that much about the pin. I care about drawing balls around that pin of ever larger radii so that I exhaust the space when I talk about Gromov-Hausdorff convergence, of which a formal definition is coming. Don't worry. But still, get that picture. In non-commutative geometry, we should have a little bit of, what should I say? I'm looking for my English word here. A little bit of a moment of hesitation. I wanted something better than that. A tremor, maybe, but that's a bit strong. Because local stuff are bad. I mean, it's a fairly generic statement, right? But it is a bit true. Fundamentally, when you go to non-commutative algebras, you lose the notion of locality in some sense. So how are we going to deal with subspace? I mean, yes, sure. I mean, I'll come back to it in a minute, but that certainly seems to be something we're going to have to be worried about. So I'm going to introduce something which I call a topography. And the idea is that it's something that I call it that because the idea is it's like making a topographic map in terms of levels. Okay. And so to do that, all I want is a subalgebra of my A, which is abelian, so that I do have locality, but just it, okay, not the whole algebra, just that thing, and contain one of those magical approximate unit I mentioned, you know, the one that with Lipschitz seminorm goes to 0. Okay, you might say, ooh, does that always exist? Yes, in a proper space, it always does. You just take your approximate unit, you just take their sum, you make a 1/2 to the n of it, you make a strictly positive element, generate the system algebra. Yes, it always exists. And not only that, but if you're in the compact case, the reason why this is not mentioned is not because, oh, I introduced something complicated. No, no, no. This would be the multiple of the unit. That's it. That's what the topography is in the compact world. So it's a replacement for that. So it's actually a fairly weak condition. It's still there on top. And I just make a remark you don't care about, but this is not new. There is a whole literature on approaching, well, exaggerate. There are some papers on things like approaching infinity inside of system algebra. There's a paper by Ackermann, Peterson, and Jacobson on that topic, for instance. I don't remember which journal, I'm sorry. And they have the same problem. If you want to talk about approaching infinity or anything like that, they choose a massa. I don't need a massa. I just need some subalgebra, some C-star subalgebra with an approximate unit. Yes, Thomas?
So this was my question. Is this topography necessarily maximal?
No. Not at all. Not at all. Not at all. In the compact case, it's just not at all. In the compact case, you could just take, in fact, it's a natural choice, a canonical choice is a multiple of the unit. That's it.
Oh, so they are very small topography.
They are small. That's right. They're not a big deal. They just replaces what we lost when we, you know, so basically in the compact case, here's one way among many to understand. In the compact case, you have a unit. So you have this special thing, the multiple of the unit, which may not seem like a big deal, but we use it all the time in the theory. In many ways, in many proofs, at some point you invoke that thing. And it's completely obvious. I mean, you don't think about it twice. But when you lose it, suddenly you miss it. And this is a replacement for my multiple of the unit. Well, those are sort of multiple of an approximate unit with a nice properties. That's all.
Another question. Are such topographies, sorry. Are massas containing topographies somehow distinguished by some property?
At the moment, I do not know. I don't know. I don't think so. I don't see any reason why they would be. I never use maximality. But you will see that when you deal with an abelian example, it's natural to take the entire algebra as a topography. It costs you nothing, at which point, it's a massa by definition. But no, I don't use maximality anywhere. My personal guess is that maybe if you did a massa stuff, you would get a sort of universality, a bit like, it's going to be a terrible, terrible way to say it. I'm sorry, but that's the best idea I can come up with. You know, when you have a manifold and you have atlas, and among all the atlases, you could take a maximal one and then forget about it. Similarly, maybe instead of dealing with many topographies, you could sort of talk only about the largest one or something. Maybe that plays a role somewhere, but I have not encountered it. To me, it plays no role, but that would be maybe something like that. Because there's a dependency on this data. And so maybe you can do something. But no, it doesn't need to be a massa at all. In my work, not at all. In fact, I tend to prefer to take it as small as possible. The way I actually, since we have people in graph algebras probably around, think of it more like a sort of choice of a diagonal. But it doesn't have to be as big because diagonals are massas, I know, but typically, but sort of like choosing a bit of a diagonal to I mean, and if you think about it in physics, it's a different idea in physics. I would say, suppose you have something like a phase space described by a system algebra, right? So you choose one particular set of observables you're going to use to scan your space, and you understand that the one that are complementary, well, they're completely diffused when you specify this one is not. So because you're a non-paved world, you have to decide which way am I exhausting my space. It's not trivial anymore, like in the classical picture. You can't go in every direction arbitrarily, right? You have to choose. So this is a very natural object, but don't think of it, it really doesn't have to be a massa. There is no role of maximality in my work at the moment. Just none.
May I ask another question? Since
Sure.
Dobrushin result is appearing now.
Well, yeah. Mm-hmm.
Yeah. So can you confirm or debunk my expectation that if you have in the classical case, if you have Rn, then Gaussians form such a family.
That's right.
Satisfying this condition.
That's right.
It is true. Okay.
That's right.
So this Gaussian family, this even universal Gaussian family on Rn, has natural topologies, just natural structure of a manifold.
Sure.
Finite dimensional manifold. So I wonder what is this natural topology of this manifold of Gaussians, and the induced weak star topology induced by this Dobrushin condition.
Well, this is interesting that you ask this. Yeah, there is a glitch, because with the structure I described, you have two ways to put a metric on that topography. One way is you take Lipschitz seminar, restrict it to M, and now it's a sort of Lipschitz seminar on a abelian thing, and you make the control-rich metric attached to it, and you have a metric. I'm not going to say Riemannian because I don't talk about spectral triple today, so I'm going to stay with the metric. But at least you could get a metric like this, right? Because you have a Lipschitz seminar. That's one way. But the other way is you could look at the state space of your topography. So the states, looking at your space of probabilities, basically looking at them as points, right? So you look at the state space of the topography, and which in the case of the Gaussian, depending how you do it, could be just if you decide they're all Gaussian centered at 0, for instance, that's just the variance. That's the only, it looks like R, right? Anyway, point is, or a covariant matrix. I don't know what version you have in mind. I mean, we can make it complicated or simple. But anyway, you look at the state space as a quotient of the state space on the whole thing, and you get the topology from that. And they don't have to agree as far as I can tell. So there are different ways. I don't know. And luckily, I don't need to know for this particular presentation. But this is an interesting issue. You have two topologies that come, and I don't know which one is the right one. Depends on what you want to do, I guess. So my guess is the quotient is maybe better, but it's, I don't know. It's a guess. I really don't know.
So thank you.
But thank you. These are good. These are all very good questions. And as I say, this is so new and fresh that there's a lot for me to think about. I'm not disputing that. But a pointed proper quantum metric space, well, it's a pinned one. Okay, so N, A, L, and mu, but you added a topography. Because really, that's what matters, this exhaustion principle. We're going to use that to exhaust our space into balls. I will say something interesting, that the biggest reason I need this was to prove the triangular equality, the abelian property, where it plays a role. It's kind of well hidden, but whatever. So, okay, now we have our class of objects. Quantum locally compact metric spaces, a choice of an approximate unit that sort of exhausts the space, and a point at which this approximate unit is sort of like centered, so to speak. And yes, I do ask mu to be a character of that topography. So it's not a character on the whole algebra. In particular, if M if A is unital and M is C times the unit, then everything is a character of that. So that's a non-condition in the compact world. It becomes necessary in the locally compact world because we need some, otherwise I hope you'll see, but it becomes unmanageable basically. Okay, I'm looking at the time. I'm going to tell you that, but I've introduced the concept of space, right? Okay. It's not that difficult. It's a C-star algebra, a Lipschitz seminorm, so the bounded Lipschitz metric gives you the weak star topology plus a couple of conditions that are secondary, a state, and a choice. This M, you could think of it almost as choosing that an approximate unit that flattens at infinity, which is in particular giving us this properness in addition to the local compactness. And I need to tell you what maps between those things are, but I only care about isometries today. So I'm only going to tell you about isometries. What's an isometry? Well, Gelfand plus, right? So you have a star epimorphism, the dual of an injection. from D to onto A, right? So you have two quantum compact metric spaces here with the topography. You know that I don't refer to the state mu. That's not accidental. It's not a type. I don't care what it does at the state mu at the moment. Just this ignores the mu. And I want it to be a star epimorphism, so that's natural. I want it to have this property that, first of all, let's see, how did I write it? Yeah, it shrinks. So when you go from, you shrink the Lipschitz norm, because you have to think of this a bit like a super, an isometry is a bit like a abstracted version of just restriction. You have a metric space, you have a subspace, you restrict. Okay? So it injects, of course, an isometry is more complicated, but at some level, it's a matter of identification. So if you do that, Lipschitz seminorm should shrink when you restrict to a subspace, right? So I asked that. And I asked this condition here, which again, if you saw some of my talk of the compact case will be familiar. If you haven't, it isn't. I'm asking for, you take this, so I don't know, the notation is reminded in this big blue box on top. This norm with an L is the max of the actual norm and the Lipschitz seminorm. And I want that to be the quotient through pi on A, I'm on the one on A, sorry, to be the quotient on the one on D through pi. This is what it says. Okay, that is the one on A is a quotient on the one on D. If I only ask for L, A to be the quotient of L by pi, then I will get an isometry for the contour of each metric. But I'm working with Forte-Mollier metrics, so this is the right way to do it. I have a green box, here it is, that says exactly that. If you have this condition, then automatically the dual map, right, at the level of the state become an isometry. So really that's natural. But then, what do I do with the topography? Well, nothing too bad. I just map the topography to itself. I mean, that's reasonable. But then I have this thing that's long, but very easy to explain. What I want is a stronger version of 0.1, but just for the topography, which in the compact case is invisible. It's for free. In the locally compact case, it's not. If I take an element downstairs in the codomain, I can lift it to an element in the domain so that neither the norm nor the L semi-norm grow too much. That's what it says. For all epsilon, I can lift it, and the price I pay is just an epsilon. Sorry, that was an accident, a mass accident. So this is stronger than 1, but it's only on the topography. Given that I had lots of very nice questions, I may have to leave it to the final questions why I need that extra condition. It's not an accident. It's there's a good reason to believe it's very much needed. But in the abelian case, you always have it. In the compact case, you always have it. So it's only new now in this talk. Literally, that's just now that we need this extra. But in the abelian case, you always have that. It's a moot condition. In the compact case, because the topography is just a multiple of the unit, you always have that. It's a moot condition. Here, what I'm saying is the following, actually. I can explain it to you really quickly. You remember that you have this approximate unit that gets flatter and flatter and flatter in A? Well, if I lift it, I want to be able to lift it through pi into an approximate of unit of D that is flatter and flatter and flatter and flatter. That's it. That's what this condition gives me, that this magical approximate lift. So in particular, if this is proper, the codomain, then the domain is proper. That's forced. Okay, this form a category. I didn't write it, but it's trivial and not, but you know, it decomposes just fine. Whew, okay. I can at last define convergence. All right, so I hope you appreciate that occasionally I give you a view of Colorado as a pose. At least Piotr, you must appreciate that.
I actually was wondering which peak is it?
I am not 100% sure, and maybe Carla remembers because I probably took that picture when I hiked with her. But I want to say that's on the way to Emerald Lake, but I'm not sure.
Yeah, yeah.
On the way, not Emerald Lake, but on the way. There's this lake before. Anyway, so appreciate. Here's Colorado.
So you think that this big white stretch is not the Emerald Lake?
No, that's not. That's one of the lake before, little pond before.
Okay.
That's exactly my point. I think this is it, but I'm not 100% sure because I know that when we were hiking, there's this bunch of snow that you have to climb over, which sometimes are okay, we're done point when it's too icy. So, but I could be wrong. And if I'm wrong, it's somewhere in the mountains nearby. Just little break from all the definitions and stuff.
Okay.
Okay, so this is the Hausdorff distance. Well, not this, it's coming in next, but this is the Hausdorff distance. But here is how you define the Hausdorff distance. You take a metric space, two non-empty subsets, and I'm going to use this hopefully clear notation that A is almost in B up to epsilon, meaning that every point in A is at distance at most epsilon from B, whereas the distance from a point to a set is written here, but probably familiar. And Hausdorff, at the latest in 1893, possibly earlier, and maybe Frédéric I've read, but I don't know. So for now, we'll credit it here. It's actually in his book. My German is terrible, so while I understand what it says, I cannot possibly pronounce it properly. So, but this foundation of set theory book defined the Hausdorff distance as such, as smallest epsilon, such that you can put A within B up to epsilon and B within A up to epsilon. Okay. And it's a nice metric when you restrict it to the closed subspace. That's collection of closed subspace is called a hyperspace. It's not my... Hence, this induces what's called a hypertopology. Now you know where the title comes from, because we're going to mimic this. And it's nice if the space is complete, then so is that. In fact, the topology induced by this is a topology, is a version of the hit and miss topology of Hypertopology. So basically, it actually doesn't depend on the metric; it depends on the topology. Very nicely behaved, and it's a big deal, right? I mean, if you do certain type of set-valued function, then you deal with this. If you do, it did have an application in image recognition. Now, of course, people would use neural nets most of the time, but you know, it's a nice subject. So now let's Gromov-Hausdorff this. So again, I have a metric space ZD for now and two non-empty subspace, but not compact or anything. I mean, locally compact would be fine because I don't, but for the definition doesn't matter. But now I choose two base points, a base point little a for A and a base point little b for B. And I'm going to do a sort of local version of what I just showed you. So it looks very similar to Hausdorff. It's the infimum of the epsilon, so sort of something about A is in B and something about B is in A up to epsilon. But what is not the entirety of A, but the closed ball of radius A, radius 1 over epsilon. So you're trying to make the ball really big, while very close to B. That's why there's an E for the epsilon, right? The smallest the epsilon is, the bigger the ball you're trying to fit. And you don't quite fit it in B, right? There's an epsilon error in your fitting. Does that make sense, this definition so far?
Mm-hmm.
And that is really close to Hausdorff, right? But it's a local version. And then we make it intrinsic, meaning we define this for any two-pointed proper metric spaces, regardless of them living into a Z. The way we do that is familiar probably. We calculate this number, this delta thing, for any possible embedding of X and Y into a Z. Okay? So this is a Gromov-Hausdorff distance. So as I say, you're trying to find a huge ball of X that's almost in Y for some isometric embedding of X and Y somewhere, and a huge ball of Y that's almost in X in that same embedding, and you try to do the best you can. And you call that the Gromov-Hausdorff distance. It's a complete metric up to full isometry. I think I said that. Yes. The slide here is exactly the same definition. I just compacted it a little bit. Anyway, so this is what Gromov introduced in 1981, as he was proving that every virtually nil put, what was it? Okay, I'm going to mispronounce it, so I'm not going to say something wrong. But its main result on groups, yes. And this was involved in things like convergence of Kerr graph and boundaries. I mean, anyway, this was really cool. It had nothing to do with manifold at the time, but it has since then entered the realm of Riemannian geometry as well, quite extensively. So we want to generalize this. All right, so this is our situation. This is our problem. I want to talk about a ball, but I want to talk about a ball in non-Kuhn geometry. All right, so I want to talk a ball with functions. All right, so the Gelfand-Naimark would say you need to use a quotient. That's out of the question. I already gave you a simple C-star algebra as an example of a locally compact metric space. we're not going to have any interesting quotient to talk of, so that's out the window. So the next thing is you could become a von Neumann algebraist and say, well, sets are projections. Okay, so this is a projection. This is a projection on a ball. You can imagine the dark blue is a graph of it. And okay, so yeah, but unfortunately, I'm insisting on working with C-star algebras, right? I mean, we don't want to start taking all this definition, put them into a von Neumann algebra. No, that is not promising. But then you say, okay, forget that. You could do something that looks like an indicator function, and you can control the slope, right? I mean, this is okay. So this is a Lipschitz element. It's 1 there, it's 0 outside, and for a while, it just goes down. Okay. But then you realize, I don't really care it's 1 on the ball. All of a sudden, you realize all I care is that I have a Lipschitz element, and 1 over the Lipschitz norm is giving me an order of scale for the radius of wherever that thing is supported, assuming it's compactly supported. Right? I mean, it's not really true because it could go back up. But that's an idea. You're like, aha. So really, what I care about, since I care about ever bigger subsets that are including balls, but are big and bigger and bigger and bigger, is really sort of like the support, so to speak, of Lipschitz function with very small Lipschitz constant will give me a huge support. So that's the idea. These pictures are an informal idea of how I'm going to do this. And so here you go. Here is a non-commutative expression of how I'm going to talk about exhausting the space with balls. So when I embed 2 quantum metric spaces into a third one, I call that a tunnel. I don't know. It's dual to a bridge. Don't ask. But essentially, I'm trying to find a common thing. So a tunnel between them is what? Well, it's that's your Z. You're going to embed, quote unquote, 2 quantum compact metric space A and B with all their data, right? You're going to embed that into a third one called D. Now, remember, we're not in geometry, so embedding is backward, right? It means I have 2 quantum isometry surjecting from D onto A and from D onto B. I define what it is, but we know that. And then I'm going to take an E. That's it, just an E. This is where the topography matters. It has to be in this topography thing. And Lipschitz. That's it. That's the data. And E is going to be that blue thing, a function like that. And then what did Gromov do? Well, he assigned a number. You know, these delta numbers, this sort of Hausdorff distance looking thing. I'm going to do the same. So I'm going to assign a number. So I take a tunnel, and I'm going to give you a number, but it's a maximum of 3 things. So let's follow. The first thing, I know the notations are heavy, but they're easy. You take the quasi-state of D. But if it worries you, start with a state space. It doesn't matter too much, but I can explain that later. Quasi-state means it's a convex combination of a state and 0. So you take a quasi-state, and I don't think I wrote it down, so I'll write it down now. What do I mean by multiplying a state by E? I mean E, phi, E, where phi is a quasi-state. It simply means this map. Okay, we all cool with that? But if I write this, then I have to, it gets 3 lines long. So it's easier to say that. You take a state, you multiply left and right by E. This pattern that I mentioned many times earlier in my talk, right? This idea of this is how you smooth things up to infinity. And then you want this to be almost included, this included up to epsilon, into the image of the quasi-state space of A. So you want to put the entirety of the state space of D inside the state space of A, but you're going to pay a small price. And the metric you use is a FRÉDÉRIC metric. Okay, so that's it. And you do that symmetrically in A and B. Then you want this E, you have to imagine the flatter it is, the bigger the support it has. It doesn't really have a support. It could be actually support on the whole space. But that's the informal idea. You want it to be very flat, so that it for sure covers a lot of space. Well, so I keep track of, it's Lipschitz in it. That's all. The 2 is just for the triangle, whatever. It's a detail. So I keep track of how flat it is. Okay. And I keep track. Okay, ideally at the pin, you may think at the pin I want it to be 1. It's a little rigid. It makes life difficult. So I'm just going to measure how far from 1 it is. And I want it to be as close to 1 as possible. You want the extent to be as small as possible when you converge. So you want to be able to shove the quasi-state space in once you smooth it out left and right like this inside the other quasi-space of the other space, and you want the Lipschitz summation to be almost zero, like the thing is almost flat. And well, you keep track of how far the pins are. That's it. You have two base points. Just want to make sure that's a detail. Okay, well, that's a number. Okay, then what do I do?
Sorry,
I take
something
the
is missing in this
yes, please.
line.
No, please. Yeah, no, I know it's a lot of things. Go ahead.
Something is missing in this third point. So the MK should be equal to something, probably, yes?
No, I take the maximum of those numbers.
Okay. Of course. Maximums of these three numbers.
Yes,
Okay.
there's three numbers and I take their max. So it could be horrible. This number could be terrible. In fact, so it can't be infinite because they're pins. And so anyway, there is this is where having this topography. But if it was infinite, so be it, arguably. I don't really care. So it could be even infinite. Whatever. It's just a number or infinity. But then this is go ahead.
You realize that it has minus 15 minutes left.
Yes, I know, but I'm going to be okay. Plus, to be fair, I answered a lot of questions, Pierre, so hopefully correctly. But actually, we're good for a little bit on that. I'm going to take the infimum of all these numbers. That's where you put them together. For every possible such embedding you can come up with, calculate this, get the infimum, which is humanly possible because in fact what it means is to prove convergence I need to find one good embedding because it will dominate this. So we're good. And okay, so I need to give a name to this. I'll get back to it in a second. The letter that you see here is an S. If you don't know what it is, it's a letter which in English used hundreds of years ago to be for this sound that mostly is found in the Anglo language, not only, but it is the primary example, the th sound, or in the or they or whatever. So that used to have a letter for it. It's a D. It looks like distance. And I like it. And I needed some symbol. Okay, so what properties does that monstrosity have? Well, it's symmetric. Okay, that's trivial. This is a good one. This is long to prove. Yeah, I feel a bit bad because this is like probably 20 pages. But you can prove that distance is zero exactly when there is a star isomorphism between the base algebras, which also is an isometry for not the Lipschitz seminorm, that's too much, but for this norm that is the max of the Lipschitz seminorm and 1/m the norm, the one that defined the Forte-Merrier. So it's an isometry for the Forte-Merrier metric. And that's where the M kind of like, well, so that depends on M. Well, yeah, in a few slides we'll deal with that. But for now, yes. But it's good. And it's an if and only, so that's very good. And it does have some sort of triangle inequality, but it's a little bit gnarly. You're going to say, oh, it went so far, so well. But this is not bad. So look at the triangle inequality. If you ignore the squares, it's the usual one, but there's these squares. So you might say, oh my God, that looks horrible. It's not horrible. Because you see what happens is this 1 plus, and that really makes a big difference, it's 1. Because what happens is if the distance, say, between the spaces is small. So for instance, B is actually a sequence and converges to A. Then every time you have the BD, so B, which one did I say? No, so that's not interesting. Suppose that D converges to A and D converges to B, then the distance from AB would be small, right? So you still have the triangle equality. You can still define a topology. I know I have 15 minutes, so I will try to tell you in 2 minutes what happens here. 1, this is in fact, even though it's not written as such, gives you something called an inframetric. It's like a metric, except the triangle inequality would be distance between A and B is less or equal than a constant times the usual thing. Okay, you can define topology as inframetric. People know about this, been studied, it's nothing new. And the way you define it maybe is worth mentioning. You define it by saying that AN converges to A by sequences, by defining a closure operator, a Kuratowski closure operator, by saying that something is the closure of a set if it's the limit of a sequence. What does that mean? It means the distance from AN to A, this inframetric, goes to 0. And that works. It gives you a topology. Usually, with arbitrary inframetric, there is a glitch. And the glitch is the inframetric may not be continuous with respect to its own topology. In particular, the balls are useless. But glory among glories, it turns out that in this case, with this red thing, that's not a problem. This inframetric is continuous with respect to its topology. So it's also the topology generated by its balls. Its ball open balls. Its open balls form a topological basis. Everything works. So it's not a triangle equality, but it doesn't matter because topologically it changes nothing. By the way, the topology is metrizable. That's true for any inframetric, it's known, but the metric is an abstract nonsense, which so if you want to, but this is slightly annoying, but it's okay. Unfortunately, as Piotr reminded me that I'm talking too long, I will not explain to you why a gnarly constant come up. You can blame Piotr. But basically, it comes from the fact that Lipschitz inequality will have all sort of nasty factors coming out. It's not going to be as simple as when you multiply two things, the Lipschitz seminorm of their product is their sum of the Lipschitz seminorm. So you have the norms playing a role, and it screws things a little bit, but not much. So that's fine. Okay. What is this? Oh, I skip all that. My 50. I wanted to explain to you some idea of the proofs. If I have questions, I can do that. Now, this to me may be enough. It may be enough. But some of you may say, there is this M. There is M. And what did M do? Remember from like way at the beginning of the talk? What happens is that when you take the Forte-Moyer distance and you restrict it to the pure state or the characters of C0 of X, where X is a metric space, what you did is you truncated the metric by M. So you only see that far. And there are easy examples of spaces that are not isometric for their initial distance, but become isometric if you do that truncation thing. All you have to do is make a gap somewhere that's too big. So, okay, that means we're not isometric for the initial distance. Maybe it's not a big deal. In all honesty, so early in the theory, I don't know. But if you don't like it, here is your candidate. This thing, which uses this little matrix, gets rid of the M by taking the inf, similar structure. And it is a nice metric. And this one is 0 up to actual isometric, like the whole initial metric, not just the Forte-Moyer, the whole thing, the Kontorovich metric. So if you want it, it exists, but it's a little, you have to, and it may look bad, it isn't. It turns out in the few examples I worked at, this is, you prove convergence for this thing easily. It's actually a lot easier than it looks, but who knows in the long run. So just so you know, this M can be handled, and that's why I didn't want to answer that early in the talk, because it's not easy. But yes, the M matters because it truncates. So it depends what kind of isometry you want when distance is 0. If you want the whole thing, you have to do something with that M, and this is what you do. Which, unfortunately for everybody, I decided to call R instead of M in this slide. So this is not a metric. It's an inframetric, but not really. It's stronger. It's a special case. And I don't have a name, and I can't call it the propinquity anymore because that's not the propinquity, even in the compact case. Slides to come. It's related, of course, but it's not the propinquity. So it's called a metametric because that's cool. And because I'm trying really hard to get grants, I'll never get. So a meta means two things. It means something that's above and beyond, like metaphysics, something that is a sort of higher level or higher abstraction. Well, this is a generalization of the metric. But also metas for the past 20 years means something about itself. Metadata is an example. So metametric is a metric about metrics. So it sort of fits. So that's what I call it. It's just a name. Can we do anything? Do I have 5 minutes left? No, I'm 8 minutes past. Can I have 2 minutes left?
You have minus 23 minutes left.
Okay, cool. So, but we already did the questions, right? So, does it work? One, if I have compact quantum metric spaces and they converge with the propinquity, do they converge for that animal? Yes. Good. Two, if I have 400 quantum metric spaces that converge for this animal, do they converge with the propinquity? Mostly yes. There is a little Leibniz property to deal with, but the answer is yes if you do it correctly. So in the compact case, we fall back on our feet. If I converge in the Gromov-Hausdorff descent, the classical picture, do I converge for this animal? Yes, I do. No problem there. In a canonical way, so to speak. Last, is there at least one example which is neither, which work. Yes. Remember that C0 of Z cross Z? Well, here are the finite dimensional approximation of it. You do C of Z mod n cross Z mod n with the same action, so to speak. And you do the same. Actually, this also comes from a sort of spectral triple, but whatever. So I define this partial derivatives, the discretized calculus. The clock matrix is the diagonal matrix with root of unity along the diagonal of order n. Anyway, if you do that, yes, the compact is a limit of those little finite dimensional things for this metric. This, as you can imagine, takes a few pages, but it is doable. So it turns out that we generally extended the Gromov-Hausdorff conjugate. That is, it works like the propinquity in the compact case. It is weaker than the normal convergence, the classical case, and it does include new examples. And that new example is a cross product. I have a few others on paper, but I haven't written them down. So too bad. You'll have to believe me. But there's the same idea. This is interesting, though, because it is a cross product. And you can essentially generalize this construction to Z acting on a proper metric space in a free, nice, proper way. And that works basically the same way. And that's it. So here you go.
Thank you very much. Okay, since it's almost sunrise, well, if you really have an urgent question, go ahead. If not, let's wind it up. So any urgent questions? I don't see any raised hands. So let me stop recording. Thank you so much for a very exciting talk.